we continue our discussion on canonical correlation analysis. We were looking at when we have actually obtained the canonical variables, then what sort of analysis can be done using those derived canonical variables. In the last lecture, at the end, what we were looking at is when we have a p-dimensional original x random vector and we have got the corresponding canonical variables, we were seeing that if we are going to express the variance covariance structure of X matrix, X and Y matrix jointly taken, then if we are concentrating on a fewer number of canonical variables, then what sort of approximation to the variance covariance matrix this k order canonical variables gives. Specifically, what we had seen in the last lecture was we had come up to this point that we had seen that this x vector, the original set of random variables, this x can be written in terms of this star 1, which is ai ui, and similarly y can be written as summation I equal to 1 to q bi times vi, where ai, these are column vectors corresponding to the A inverse matrix. A inverse matrix was defined as the matrix which was having the following structure. So, this A inverse matrix was this sigma 1 1 to the power half E1 and so on. So, the ith column here of A inverse matrix was sigma 1 1 to the power half, and hence if we consider only first k canonical variables, here k is say less than p or less than or equal to p if we are taking the entire set of variables in the canonical variables, then x star can be written x star, which is x reconstructed using the first k canonical variables, then that x star is I equal to 1 to k ai ui, and similarly y star is equal to I equal to 1 to k bi times vi, right. And using those two representations x star and y star, we see that the covariance matrix of x star is represented as this, which is summation I equal to 1 to up to k only, where k is the number of canonical variables chosen, ai prime, and similarly this y star is equal to this. Otherwise, this y corresponding to this form here, what we can write is summation I equal to 1 to up to q this bi vectors, which is the original form of the y vectors, bi into vi. Now, from here this covariance matrix of y is straightforward to obtain, which is summation I equal to 1 to q bi vector and the transpose of the bi vector. Now, these are the constituent facts, and the covariance of y star, which is this summation truncated at the point k, would be given by the corresponding sum as in I equal to 1 to k, which is bi transpose again, right. And if we now concentrate on what is the covariance matrix between x and y, well, the covariance matrix between x and y was covariance matrix of x, covariance matrix of y, and this is the covariance matrix between x and y, and this is the transpose of this element. So, this is covariance matrix of y with x. This in terms of our original definition is this sigma 1 1 matrix, sigma 1 2 matrix, sigma 2 2 matrix, and sigma 2 1 matrix. Now, we have obtained this sigma 1 1 and sigma 2 2 in terms of this ai and bi vectors. Let us also see what this covariance between x and y is. Covariance between x and y is in terms of the new notations, that is what we had introduced, that x is equal to A inverse u and y is equal to B inverse v, x is equal to A inverse u vector and y is equal to B inverse times this v vector. This is p by 1, this is q by 1. So, the covariance matrix of this is going to be given by A inverse times the covariance matrix between U and V. We have seen it time and again that what that is equal to. This is rho 1 star, rho 2 star, rho p star. These are the p canonical correlation coefficients that augmented with zeros, right. So, this is the first p by p block wherein we are able to pair ui with vi, and these are ui with v p plus 1 to up to vq. So, these are those columns here that multiplied by this b inverse. Now, in terms of these ai vectors and bi vectors, what we can write, so this will imply that the covariance matrix between x and y, which is of course sigma 1 2, that can be written as this is a 1 vector, a 2 up to a p vector, this multiplied by that matrix which we had taken, this rho 1 star, rho 2 star up to rho p star here. All other entries are zeros, that augmented by this b 1 prime b q prime, right. So, this is what it is coming. This is B inverse is transpose, because this inverse is coming on the other side. So, it is the transpose of that, and this is what? This is summation I equal to 1 to up to p a I vector, that multiplied by, well, this rho I stars are all scalar quantities. So, I can write this rho I star in here, that multiplied by the corresponding B I transpose. That is, this covariance matrix between x and y is finally of this particular form. Now, if we follow this same approach, then the covariance matrix between x star, the x vector approximated using the first k canonical variables x star and y star, note that nothing much changes, except in here we will be truncating this up to the kth row here, and we will be truncating this matrix up to the kth, this we are truncating here up to the kth column, and here on the right hand side we are truncating up to the kth row here. So, that would lead us to summation I equal to 1 to up to k rho I star a I into B I transpose. So, what's that we are having? The original sigma matrix now, in terms of this a I b I vectors, this element is summation I equal to 1 to p a I transpose. The 2th entry here is I equal to 1 to up to p b I transpose, and this entry here is I equal to 1 to up to p rho I star times a I into b I transpose, and this is just the transpose of this particular entry here. So, that is the covariance matrix in terms of this a I and b I vectors, and when we are looking at only k canonical variables, then this matrix is what is now giving us the covariance structure. So, this is now I equal to 1 to up to k, the same terms actually, only the summations are having up to the kth terms. So, this is a I transpose, this one is summation I equal to 1 to up to k rho I star a I b I transpose, this is summation I equal to 1 to up to k b I transpose, and this one is just the transpose of this particular entry here. So, when we have approximated or rather when we have just used k canonical variables, then we look at how good is that k number of canonical variables by looking at the closeness of the respective entries here. So, we check how close is this sigma matrix to the new sigma matrix defined through the k canonical variables, and hence we check how close is this with this particular entry here, 1/1th block here, how close is this 1/2th block here with this, which is using just k terms, and how close is this term here, the 2/2th block, with this particular entry here. So, that is what is the technique to check for the closeness of approximation. We check how close the matrices. There are 3 crucial matrices. I will write it as I equal to 1 to k plus 1 to up to p, AI transpose, summation I equal to k plus 1 to up to p, BI when we are looking at this is up to q, this is BI transpose, and the cross block here, which is summation I equal to k plus 1 to up to p rho I star AI BI transpose are 2 null matrices. If these 3 matrices are close to null matrices, then what will happen is that well, this summation here is up to q, because BI transpose has q entries. So, if we have these 3 matrices close to null matrices, then what we will be having is this matrix here close to this particular matrix, because the term that we are not considering, that is I equal to k plus 1 to up to p here, I equal to k plus 1 up to q in this entry, and I equal to k plus 1 to up to p in this entry here, will be close to the null matrices, right. And that this technique actually provides us a way to check whether k number of canonical variables is enough to explain the covariance structure of the original set of random variables. Now, we make the following 3 important notes here. The first note is, what we expect is that typically the third matrix here, I equal to k plus 1 to up to p rho I star AI into BI transpose, will be closer to null matrix, to a null matrix, than the other 2. The other 2 being a summation from k plus 1 to up to p AI transpose, and the summation I equal to k plus 1 to up to q BI transpose. This is so because this is so as usually k is to be chosen such that rho star k plus 1, and hence rho star k plus 1 onwards, that is rho star k plus 2 up to rho p star, are negligible. This is so because if we choose our k, the number of canonical variables to be retained, in such a way that the eigenvalues, the square root of the eigenvalues of that sigma 1 1 to the power minus half, sigma 1 2, sigma 2 2 inverse, sigma 2 1, sigma 1 1 to the power minus half, that matrices eigenvalues are rho I stars. So, if we choose rho star k plus 1 onwards, because it is in order to be negligible, then what will happen is that this particular matrix, since rho k plus 1 star, rho k plus 2 star, rho p star, all of these are negligible and close to 0, this third matrix here, which is the cross block matrix, this one will typically be close to a null matrix, but that cannot actually be said about the first 2 blocks, the 1 1th block and 2 2th block, because simply because those does not involve this rho I star, which are negligible, and that is basically the guideline of choosing the number of canonical variables that we are going to retain, right. So, typically this particular matrix here, the cross block here, which actually looks at this covariance between x and y, and that reconstructed through x star and y star, that particular block will be having a closer approximation to the original sigma 1 2 matrix. Now, as a second note here, we just, it is a small note, we have already obtained what is the covariance between x and u and also the correlation between x and u. Let us see that this particular matrix here, the covariance matrix between x, the original set, and the canonical variables derived from the x's, both are p dimensional. So, this is in terms of the A matrix, we can write it straight away as that equal to the A inverse matrix. Why? Because x is equal to A inverse u according to our definition. So, this A inverse, which we had denoted by these column vectors A1, A2 up to AP, these P column vectors, these column vectors has got the interpretation that this is covariance between x1 and u1, this is covariance between xp and u1, and so on. So, this A1, which is the first column of the A inverse matrix, the first column of x and u's covariance matrix, that holds all these entries here, and similarly all the other columns can be filled up. So, this is covariance between x1 and up, and this last entry is covariance between xp and up. So, these are all the entries. So, this particular column is what we have as the A1 column, and the last column, the pth column here, is what is that AP vector. This is in the other way definition, this is equal to this one, is equal to sigma 1 1 to the power minus half times E1, right. The third note says that suppose we consider k strictly less than p canonical variables, as is the setup in the present situation, then these canonical variables are just u1, u2, up, let me just uk, let me write that u1, u2 up to uk, then the proportion of the total variance of x, this is the first set of variables. So, the proportion of the total variance of x explained by this k canonical variables u1, u2, uk can be quantified by the following expression. Now, how are we going to say this particular proportion? The logic behind quantifying this proportion of total variance, well, what is the total variance? The total variance is in x is corresponding to the trace of the variance covariance matrix of this x. So, that is trace of sigma 1 1. So, this is the total variance. Now, this is going to be having a numerator if we are going to measure the proportion of total variance in x, that is explained by u1, u2, uk. This would be given by the reconstruction formula. So, that this is equal to summation I equal to 1 to up to k ai transpose. So, this one is what? This one is the covariance matrix of x star. X star denotes that reconstructed x using u1, u2, uk, the k canonical variables, and hence the total variation in x star can be measured by this quantity, which is trace of this matrix. This is nothing but the covariance matrix. So, just to recall that this is nothing but, as we are denoting this by the trace of the covariance matrix, this is the trace of the covariance matrix of x star reconstructed using the k canonical variables, that divided by the trace of the original covariance matrix, that is, I am sorry, this is the original covariance matrix, which is x. this trace of covariance matrix of X is nothing but trace of sigma 1 1, and covariance matrix of X star was given by this if we are retaining up to k canonical variables. So, that gives us the trace of this particular quantity. So, this is how we can quantify. Now, we can get down a bit further and see what is this trace of AI prime matrix in terms of these covariances. Now, as we can see that this A inverse, which we have denoted in the previous slide as A1, A2, AP, which was that covariance matrix of X and U. So, this would imply that this AI vector is the ith column of this covariance matrix. The ith column here is the ith column here. So, that would be given by covariance between X1 and UI up to covariance between XP and UI. So, this is going to hold these elements, which is covariance between X1 and UI 2 up to covariance between XP and this ith canonical variable. So, this is for I equal to 1 to up to P. So, what we are considering is this up to this term. So, if AI is equal to this will imply further that AI transpose AI is just going to hold these square entries. So, it is Xj and Ui covariance square of this and summation j equal to 1 to up to P, right. So, this is what we are going to have. So, this will imply that summation AI, which is going to play a role in that proportion, AI transpose AI I equal to 1 to up to k, the order of truncation. This would be given by summation I equal to 1 to up to k, summation j equal to 1 to up to p, this covariance between Xj and Ui, this whole square, right. So, that this will imply that this term that we were considering, let us write this as star term. So, this star term, which was equal to the trace of the summation I equal to 1 to up to k AI vector into the transpose of that AI vector, that divided by trace of sigma 1 1 matrix. This is going to be given by, now trace, you can take trace of sum equal to sum of the respective traces. So, what this is going to be? This is going to be I equal to 1 to up to k trace of AI transpose, that divided by trace of sigma 1 1. You can further write trace of AB equal to trace of BA. So, that this is equal to I equal to 1 to k trace of AI transpose into AI, that divided by trace of sigma 1 1. Now, AI transpose AI is a scalar quantity, and hence this is just equal to summation I equal to 1 to up to k AI transpose into AI, which we have just now computed, divided by trace of sigma 1 1. So, that this term is equal to summation I equal to 1 to k summation j equal to 1 to up to p covariance between Xj and Ui square, this divided by trace of sigma 1 1. Well, this trace of sigma 1 1 can also be written in terms of such covariances. Recall that this sigma 1 1 matrix in terms of AI vectors is just equal to AI. So, we recall that this sigma 1 1, which is the covariance matrix of X, is nothing but in terms of these definitions, that is AI transpose I equal to 1 to up to p. So, this is what we have, and hence this one further can be write as summation I equal to 1 to up to k summation j equal to 1 to up to p. This is covariance Xj and Ui square, that divided by once again the double summation, wherein the first summation I will be equal to 1 to up to p, j equal to 1 to up to p, that divided by the same term covariance Xj and Ui square. So, this is a crucial thing which actually tries to explain the proportion of total variance in the first set of variables, that is x, in terms of only the k less than p canonical variables. So, if this is the expression, we can similarly obtain the expression for the second set as similarly the proportion of total variance in the second set, total variance of the second set, that is y set of vectors, explained by the retained second set of canonical variables, which are v1, v2, vk, would be given by trace of that summation I equal to 1 to k once again of bi transpose entries, that divided by the trace of the covariance matrix of y, which is trace of sigma 2 2, right. Now, as in the previous example, one can reduce it into this particular form. So, this is going to be given by summation I equal to 1 to up to k, let me write this as summation I, right, summation j equal to 1 to up to q, and then this is going to be given by covariance between yj and vi, this whole square, that divided by trace of sigma 2 2, or once again this trace of sigma 2 2 can be written in terms of this covariance square terms, and this can thus be written as summation, the numerator does not change of course, I equal to 1 to k and summation j equal to 1 to q, because q is the order of y random vector. So, this is yj and ui squared, that divided by summation I equal to 1 to q now, because we are looking at the entire x and its covariance matrix as sigma 2 2. This is summation j equal to 1 to q, and this is covariance between yj and ui square once again. So, these two quantities are crucial in looking at how much of the total variation in the respective sets actually x's and y's are explained if we are retaining only k canonical variables in the process, right. Now, let us look at an example, a numerical example, to see how this actually works, the concept that we tried to learn today. So, let us take that previous row matrix with which we had obtained the canonical variables. So, that had got this structure, that it was the correlation or the covariance matrix of that 2 by 2 standardized variables, which had values as 1, 1.4 as the first block here. The second block was given by 0.5, 0.6, 0.3 and 0.4, and this block here is row 2 2 block is 1.21, right. It is a symmetric matrix. So, this entry is as the transpose of this, and this entry is of course 0.4, and this one is also 0.2. So, we have p equal to q equal to 2. Now, let us take, as in the previous example, as we had seen in the previous lecture, that this matrix has got the corresponding canonical correlation coefficients, the first one significant and the second one was negligible actually. So, that rho 2 star was equal to 0.03 if you recall. So, we are going to neglect that particular term and take, let us take this k equal to 1, and we will say that since the second canonical correlation coefficient was negligible, we are only going to retain one canonical variable. We had earlier obtained the two canonical variables associated with k equal to 1 as the following. I will just write those canonical variables. It was 0.86 times x1, the first original variable, this in plus 0.28 times x2, and v2 was computed as 0.54 times y1, this plus 0.74 times y2, right. So, this is what we had derived earlier. Now, using this, of course, it uses this A1 vector transpose, that to be equal to 0.86, which is the coefficient vector here, 0.86, 0.28, and this B1 vector was 0.54, and 0.74. These are the two terms. Now, this from this expression here u1 and v1, what we can compute is what is the covariance between x1 and u1, that is straightforward. So, what this will be? This will be 0.8 times covariance between x1 and x1. Now, these x's were standardized actually. So, this covariance will be equal to 1, this plus 0.28 times the covariance between x1 and x2 whatever. So, this covariance between x1 and x2 is going to be this 0.4, covariance between x1 and x1, that is the variance, is equal to 1. So, this turns out the numerical value of this covariance between x1 and u1 turns out to be, it is 0.972. Now, similarly, one can compute the other term, this covariance between x2 and u1 will turn out to be it's having a numerical value 0.624. Now, why are we computing these two terms from the canonical variables covariance x1 and u1 and covariance between x2 and u1? Because we want to construct that a upper 1 vector. If you come back to this particular point here, that this a1 is what? It is the first vector associated with covariance of x1 and u1, xp and up. So, that is the first column of this A inverse matrix. And why is that required? That is required essentially in order to look at these quantities, which is going to tell us about the proportion of total variance in x and in y later on. That is being explained by the first canonical variable u1, canonical variable pair u1 and v1, right. So, once we have these two, we have the A1 vector, A upper 1, that is the first column of the A inverse matrix. So, this has got the entries that we have computed. These are the two quantities, right. Now, similarly, this B1 vector can be computed. Now, this B1 vector will hold the first entry here will be covariance between y1 and v1, and the second entry will be covariance between y2 and v2. So, given the form of v1, this one can find out what is the covariance between v1 and y1, v1 and y1 and v1 and y2. This is covariance between y2 and v1. This can be computed once again looking at the form. So, the numerical value of this turns out that this is 0.688 and this is equal to 0.848. Now, using this A1 and B1 vector, one can compute what is A1 transpose this particular matrix. So, this matrix turns out that it has the following entries, which is 0.945, 0.607, this is 0.607, this is 0.392. Now, similarly, from this B1 vector, we can obtain this B1 transpose matrix, which turns out to have the following numerical values, which is 0.473, 0.583. This is of course a symmetric matrix, no need as such to write these off diagonal entries. So, this B1 transpose and B1 transpose and A1 transpose are the two matrices which are going to approximate what? This A1 transpose is that proportion in summation AI transpose, summation AI transpose, summation I equal to 1 to up to p is actually giving us the covariance matrix of the original set of random variables. And if we are looking at only one canonical variable, that is if we are choosing k equal to 1, then A1 transpose, this is that sum, summation I equal to 1 to k we are choosing as 1. So, it is that portion which is actually going to approximate the original sigma 1 1 matrix, and this B1 transpose is that portion of the covariance matrix of y, which is just going to explain the covariance structure of the second original set of random variables, which is the vector y, having the covariance matrix as sigma 2 2, here we have rho 2 2, and we also need to compute another term which is the off diagonal term. Let me also write that off diagonal term first. Also this rho 1 star A1 B1 transpose. Why are we looking at that? Because if we recall that in the off diagonal block we have summation I equal to 1 to p in the original set of random variables. So, the covariance matrix between x and y is in the off diagonal block, which is summation I equal to 1 to p rho I star A I B I transpose. Now, we are truncating the numbers or number of variables at k equal to 1, we are choosing only one canonical variable, and hence this is one, this is the matrix which is having the numerical values as 0.495, 0.610, 0.310, 0.391. This is that portion which is going to approximate the rho 1 2 block there. So, what we are going to have thus, if we consider only one canonical variable pair, as in the present situation u1 v1, then this matrix here what we have obtained, I will have to write these numerical values once again. So, these numerical values here 0.945, 0.607, 0.607, 0.392 approximates, this is that portion which is explained through the first two canonical first pair of canonical variables, this as approximating this block here which is the rho 1 1 block. So, that is one which is trying to approximate 1.4.41, that is number 1. This is one which approximates this. Now, what we can see is that this matrix, while we are considering one pair of canonical variables, as such is a poor approximation of the original matrix. So, this is a poor approximation. Now, the second 2 to 8 block, if we look at the 2 to 8 block which is B1 B1 transpose, that particular matrix has numerical values as this 0.719, this as approximating the rho 2 2 block. Now, the rho 2 2 block has entries 1, 0.2, 0.2, 1. So, once again we see that this B1 B1 transpose matrix as such is a poor approximation of this rho 2 2. So, this is a poor approximation. However, if we are now looking at the off diagonal block, the off diagonal block has entries. So, after these two what we see is the third approximating matrix. The third approximating matrix is what we have obtained in here, which is rho 1 star A1 A1 B1 transpose. So, that approximation is what we have the numerical values as 0.495, 0.610, 0.310, 0.391. This as approximating which quantity? The rho 1 2 matrix. This as approximating the rho 1 2 entry, which is 0.5, 0.6, 0.3, 0.4. Now, in contrast to the two previous approximations which we had seen that this was trying to approximate rho 1 1, this matrix B1 B1 transpose trying to approximate this rho 2 2 matrix, and this matrix here trying to approximate the rho 1 2 matrix. While the two previous approximations were quite poor, this is a reasonable approximation. This actually highlights that the note number 1 that we had written here, if we go back to that particular note here, we had said that typically what will happen is that this matrix, the residual matrix, will be closer to the null matrix, that is summation I equal to 1 to k will be a closer approximation to the corresponding matrix, which is sigma 1 2 matrix, than the other two matrices, which are the rho 1 1 or sigma 1 1 and rho 2 2 or sigma 2 2 matrix. This is what it is basically highlighting, that although we had poor approximation of the two previous matrices, this is a reasonable approximation. Now, the third note what we had done today is the proportion being explained by the first canonical variables, first pair of canonical variable. This u1 would explain the trace of a1 transpose here, because k is equal to 1 here. So, this is trace of this matrix, this divided by trace of sigma 1 1 or rho 1 1, whatever it is, the starting matrix. So, for the given problem, this trace turns out that this is equal to, I will just write it, the values here, that is 0.945 plus 0.392, that divided by 2. So, this approximately is explaining 66% of total variation in the original set of random variables x1 and x2. This is a reasonable amount which the first canonical variable is explaining, and similarly this V1 explains this trace of B1 transpose matrix, this divided by the trace of sigma 2 2 matrix. This further can be obtained, or rather the numerical value turns out that it is 60% of the total variation in y vector, right. Now, in this example, this is the covariance matrices corresponding to the standardized variables, and hence this sigma 1 1 and sigma 2 2 are actually rho 1 1 and rho 2 2. So, this is how for a given problem one actually can see how close will be a particular order of canonical variable pairs chosen, that is the k term in this approximation, and how close will the corresponding approximations to the variance covariance structure of x be if we are considering up to k canonical variables. And also by considering those many canonical variables, what is the proportion of the total variance in the first set, what is the proportion in the variance in the second set of variables, are getting explained through the retained number of canonical variables. Now, to end this concept and to end this lecture series, what we are going to just look at is, in this canonical correlation analysis, how we are going to have the sample canonical variables and the canonical correlation coefficients, because that is what we are going to have in practice. So, in practice what we are going to have is a data which might look like the following, that it is Z1, Z2, Zn. So, we have n data vectors. Each of these data vectors has got two components, x and a y component. So, this is the first observation corresponding to the x set of random variables, and this one is the nth set here, which we denote by xn, and this is yn. Now, we assume that this x here is p by 1 set here, and this is q by 1 set here. So, this is the original set of random variables, the first set, the second set p by 1, q by 1. So, each of these zi's are actually p plus q by 1 random vectors. Now, given these two sets of random variables observations and n replications of that is the sample size, n is the sample size, how we are going to calculate the sample canonical correlation coefficients and the corresponding sample canonical variables. Now, given this set data set here, what we can compute is the x bar vector, the sample mean random vector, corresponding to the first set of random variables. So, that is equal to this summation I equal to 1 to n of xi's, and similarly this y bar can be computed. This is 1 upon n summation I equal to 1 to n of these q dimensional observations. Now, once we have these two, we can also calculate the sample covariance matrices respectively for the respective components. Now, S11 is one that is going to be computed from x1 vector, x2 vector, xn vector, and that, let us consider that we are considering this 1 upon n minus 1 as the divisor, which is going to correspond, as we have seen in the theory, that this is the unbiased estimator. So, this is summation j equal to 1 to n xj minus this mean vector, xj minus this x bar transpose, S22 matrix, which is a sample covariance matrix, variance covariance matrix corresponding to the observations y1, y2, yn random vectors observations. So, summation j equal to 1 to n once again of this yj vector minus the corresponding y bar vector, yj vector minus this y bar vector transpose, and also the covariance matrix, the sample covariance matrix. This is once again with a divisor 1 upon n minus 1. This is summation j equal to 1 to n xj minus x bar into yj minus y bar transpose. So, we will have corresponding to this random variables x and y will have the sample variance covariance matrix, is now given by this S11, S22, S12, S21. So, this is now the sample variance covariance matrix. Now, from here, how are we going to define the sample canonical correlation coefficients? We will see how that is given. So, we will first write the definition. So, the first pair of sample canonical variables the first pair of canonical variables is given by, this is u1 hat, which is given by a hat times a hat transpose times x, and v1 hat, we are using the same notation still and putting a hat in order to indicate that they are some sort of estimated components. This is b hat prime y. This u1 hat and v1 hat is such that the sample correlation coefficient between a hat prime x and this b hat prime y is maximum. That is, we are looking at maximum over a and b, the two linear combining vectors of the sample correlation coefficient between this a prime x and b prime y. So, this one is going to be the optimum value, optimum linear combining vector here. u1 hat and v1 hat will be with the optimum coefficients here. So, a1 hat or rather a hat is that a vector and b hat is that b vector, which is going to maximize the sample correlation coefficient between these two linear combination comprising of x's and y's, with of course, the restriction that with the sample variance of a hat prime x and b hat prime y equal to 1, right. So, that is basically the similar type of situation that we had seen for the population canonical correlation coefficients computed from the sigma matrix. When we had sigma matrix, then we had also considered a prime x, b prime y, and then we tried to find out that linear combining vector A hat A and B such that the population correlation coefficient between A prime x and B prime y is going to be the maximum among all such linear combinations, with the restriction that the variances of u1 and v1 will be equal to 1. Now, when we are looking at the sample counterpart, we are also having the same philosophy that you look at all such linear combinations with the condition that the sample correlation coefficient between u1 hat and v1 hat would be the maximum, subject to the condition that the sample variances of a1 prime x and b prime y will be equal to unity. Now, we will have the similar definition for the second and onwards canonical variable pairs, which we are going to give. Well, with that, the sample, we should also say that the sample correlation coefficient between these two linear combining vectors A hat prime x and B hat prime y is the first canonical correlation coefficient that can be derived from the data, and in general the kth pair of canonical variables say given by u k hat and v k hat. So, this is the kth pair of sample canonical correlation variables, I should say the kth pair of sample canonical variables. This is such that the sample variance of this u k hat and v k hat, sample variances of a k hat and b k hat is equal to 1, and the sample correlation coefficient between this u k hat and v k hat is given by the maximum over A and B of all possible sample correlation coefficients between A prime x and B prime y, subject to the condition, to the two conditions. Number 1, that the sample correlation coefficient between this A I prime, A I hat prime x, let me just write this as A prime only, A prime x and u I hat will be equal to 0 for every I equal to 1 to up to k minus 1, and number 2, the sample correlation coefficient between B prime y and V I hat will also be equal to 0 for every I equal to 1 to up to k minus 1. So, this basically translates that concept of the population correlation coefficient, canonical correlation coefficient, in terms of the sample canonical correlation coefficients, because as you can see here that the sample correlation coefficient that we are going to define for the kth pair of canonical variables is that this u k hat and v k hat are going to be such that this is a kth pair of sample canonical variables are going to be such that the sample variance of each of these quantities will be equal to 1, and the sample correlation coefficient between u k hat and v k hat is of course such that it is going to maximize over all possible choices of A and B, such that the sample correlation coefficient between the linear combining terms A prime x and B prime y is going to be the maximum, subject to the condition that we will be having the sample correlation coefficient between this A prime x at the kth step uncorrelated with all the previous k minus 1. So, this u I hat are the previous k minus 1 canonical sample canonical variables. Now, these are going to be uncorrelated with the previous k minus 1 terms, and we are also going to have this being satisfied that B prime y, all such b's such that those B prime y's will have the sample correlation coefficient with Vi hat for every I equal to 1 to k minus 1, all previous k minus 1 canonical variables obtained through the linear combining Y will also be equal to 0. Now, if we have defined this sample canonical correlation coefficients in this particular way, the last thing that we will be doing is we will just look at how these are going to be done in relationship with the S matrix that we have as a sample variance covariance matrix this, and it turns out so that it is exactly the similar type of expressions that we are going to get, we had actually got when we had considered the population correlation population variance covariance matrix as sigma. So, with this definition of sample canonical variables and the sample canonical correlation coefficients, we will just look at how to compute the sample canonical correlation coefficients and the sample canonical variables. Now, let this rho 1 hat star square greater than or equal to rho 2 star hat square up to rho p hat star square be the eigenvalues of the matrix which is going to play the same role as the corresponding matrix in the population setup. So, it is S11 to the power minus half, S12, S22 to the power minus 1, S21, S11 to the power minus half. So, suppose these are the ordered eigenvalues of this particular matrix with corresponding orthonormalized eigenvectors as E1 hat, E2 hat and EP hat. The reason why we are putting hats here is that we are looking at the estimator of this quantity from the sample variance covariance matrix. The eigenvalues are denoted by hats, the eigenvectors are also denoted by the corresponding hat vectors. Further, let this F1 hat, F2 hat and FQ hat be the eigenvectors orthonormalized, once again of course orthonormalized eigenvectors of S22 to the power minus half, S21, S11 to the power minus 1, S12, S22 to the power minus half matrix, where the first P of F1 hat, F2 hat, FQ hat will be proportional to, similar to the population setup, will be proportional to S22 to the power minus half, S21, S11 to the power minus half times Ek hat, because the first P non-zero eigenvalues of this matrix, which is S22 to the power minus half, S21, S11 inverse, S12, S22 to the power minus half will be same as the corresponding P non-zero eigenvalues, the largest eigenvalues of this particular matrix, and the corresponding orthonormalized eigenvectors, first P of them, the corresponding to the first P largest eigenvalues of this matrix will be proportional to this particular element here. The kth sample canonical variables are going to be given by UK hat, which is going to be given exactly in the same way as to what we had done for the population term. So, it is going to be Ek hat times S11 to the power minus half times this x vector, and Vk, the kth estimated sample canonical variable, is going to be given by f k hat vector S22 to the power minus half times this y vector. So, this actually gives us a way to compute the sample canonical variables in pairs. Now, it has a striking resemblance of course with what we had for the population setup. For the population setup, UK, the kth the first component of the kth canonical variable was given by, if you recall, Ek times sigma 1 1 to the power minus 1 times this x vector, and Vk was given by this Fk vector times sigma 2 2 to the power minus half times y vector. So, what we are doing here is just using the corresponding estimates and getting all the k canonical variables. Now, all the results actually that what we had done for the population canonical correlation coefficient and the corresponding canonical variables, they are applicable for the sample setup. In particular, the important things of course what we are going to write in here. Now, after this of course one just will recall that when we had rho 1 star square, rho 2 star square, rho p star square as the population canonical correlation coefficients, the canonical correlation coefficients here, the kth canonical correlation coefficient will just be equal to rho k star hat. So, before we proceed to the note, I will just say that the kth sample canonical correlation coefficient, the sample canonical correlation coefficient is given by rho k star hat, right. Now, we go on to this last few notes here, that once this sample correlation sample canonical variables are constructed, the sample variance of u k hat and v k hat can be easily shown to be equal to 1. They are equal to 1. This follows from the orthogonality of E k hat vectors and F k hat vectors. Then sample correlations between these constructed terms, say R u L hat and u S hat, this is going to be equal to 0 for every L not equal to S. Sample correlation between u L hat and v S hat, say, will be also equal to 0 for every S not equal to L. This sample correlation coefficient between u L hat and the corresponding V L hat, this will be equal to rho L hat star, and the similar terms can also be filled up. This is, say, between V L hat and V S hat, this will be equal to 0 for every L not equal to S, and so on. So, this is these similar type of results we had also got for the population quantity as well. Now, the third note is what we will say, that the matrix of sample correlations between the original variables and the canonical variables, between the canonical variables and the original set of variables, remember we had a similar expression for the correlation matrix between the canonical variables and the original set of variables, that is rho u and x or rho v and y and other combinations in the population setup of the canonical variables. Now, in case of the sample canonical correlation canonical variables, the sample correlation matrix between these canonical variables and the original variables can similarly be obtained. So, they have the following form, with the entire set of sample canonical variables, say u hat, which would be given by a hat times this x vector, and v hat would be given by this b hat times this y vector. This is going to be our p by 1 vector, this is going to be our q by 1 vector. So, the sample correlation matrix between u hat vector and this x vector would be given in a similar expression to that of the population quantities, with S11 taking the place of sigma 11 and D11 matrix taking the place of V11 matrix, where this D11 is the diagonal matrix which is computed by choosing the diagonal elements of the S11 matrix, and we will also have the correlation matrix between the other quantities, say the correlation matrix of V hat vector with Y vector. So, this Y vector also is that original set here. In analogy with the population terms, this will just be given by S22 matrix, and this will be given by the D22 matrix to the power minus half, wherein this D22 matrix is the diagonal matrix which holds the diagonal entries of the S22 matrix. We also have the cross terms, which is the correlation matrix between U hat and Y vector, that would be given by A hat times S12, which is taking the place of sigma 12 matrix. This is multiplied by D22 to the power minus half, and the last thing is that the correlation, the sample correlation matrix between this V hat vector and the X vector, that would be given by this B hat matrix, that multiplied by the S21 matrix, that post multiplied by D11 to the power minus half. So, all the next set of other results and how to do these computations, they follow exactly in the same way as to what we had done for the population canonical correlation variables, which we had started using either the sigma matrix or the rho matrix. Now, here we have the sample estimate, the estimated sample variance covariance matrix S, and as we see in these notes, all the things that we had done for the population canonical variables, they are exactly, they follow exactly in the same way for the sample canonical variables pairs and the sample canonical correlation coefficients. So, all these results actually just reminds us that we basically had the similar type of expression for the population, where S11 was in place of S11 we had sigma 11 and so on. So, this thus concludes actually this particular course on applied multivariate analysis. So, for further queries one can contact the instructors of this particular course. The instructors, I am Amit Mitra, and my co-instructor in this course was Sharmishta Mitra. One can contact us on our email IDs for any queries, any clarification regarding any lecture in this course. This is email ID of my co-instructor at iitk.ac.in. One can also contact us on our department address, Department of Mathematics and Statistics at IIT Kanpur. So, this concludes this course on this video course on multivariate applied multivariate analysis. Thank you.